Okay, so let's talk about this section. I think this section isn't that hard. It's nothing like new, like we're not learning any like new topics in this section. And every step is like relatively easy. Like we're either setting something equal to 0 and solving for x, or doing something simple like that. But I will say that this is probably that's the biggest chance for you to make like random mistakes because we're plugging things into different functions. And sometimes it's hard to figure out if we're plugging something into the original function, if we're plugging something into the derivative. And then soon we're going to start talking about the second derivative too. So there's 3 different functions that we can be working with. And it's kind of hard to figure out, okay, am I working with this function, the derivative, or the second derivative? And it's kind of hard to figure it out. Okay. Now, I told you that I will give you the tools to memorize what to do in each question. But honestly, instead of memorizing, it's a little bit easier to just kind of think about what you're doing. Because if you think about it, it kind of takes away from memorizing what to do in each question. As long as you think about, okay, increasing, decreasing means the first derivative, concavity means the second derivative. When you think of it in context of what's actually happening, you don't actually have to memorize what to do in every single type of question that I'm asking. Okay, so I'll give you the tools to memorize it, but I recommend not memorizing it, just thinking about what's actually going on. Okay, so we talked about a few things. We did the increasing, decreasing test. I think I wrote your hand off last week, copying down all this stuff. We talked about the first derivative test, and then some of these tests required you to think about discontinuities. Some of them didn't, right? First derivative test, we just thought about critical values. Then we talked about finding local mins and maxes. So that involved the first derivative test. And then we kind of left off at this area here. Okay, so over here, I kind of introduced the idea of concavity a really long time ago. Okay, and is there someone that can explain the difference between concave up versus concave down? So what's the difference between those two? Michael?
Concave up is takes enough gravel.
Mm-hmm.
Concave down is not.
Yeah, perfect. Concave up means, well, it's shaped like a cup, right? Concave down means it's shaped like a frown, right? So it's pointing up or the curve is pointing down. Okay. Now, another thing about concavity that we talked about is when the second derivative is positive, we're concave up. And when the second derivative is negative, we're concave down. Now, there's some points where the second derivative is 0, and not just equal to 0, but we're switching from being concave up to concave down. We had a special name for that, and we called it a point of inflection. Okay, so a point of inflection is when we switch from concave up to concave down, and the second derivative is equal to 0. Okay, I think we did a little activity a long time ago where we talked about, okay, what does the function look like when it's concave up? What does it look like when it's concave down? And increasing, decreasing, things like that. I'm not going to spend too much on this. We'll see this happen in our examples, but this is just a reminder of what we did with concavity last time. All right, let's go into a few tests that we'll learn how to do here. The first one is called the concavity test, but it's really just the definition of concavity. It's telling us that if the second derivative is positive, then it's concave up. If the second derivative is negative, then it's concave down, which we already talked about, okay? We also have the definition of an inflection point, okay? And technically, what an inflection point is, well, when the function is continuous, when the second derivative is 0, and we're switching from being concave up to concave down, or concave down to concave up. So when the second derivative changes signs, that's what we're calling an inflection point. Okay, so we have this graph here, and I really like this graph because it shows a lot of different things that can happen here. So let's just talk about concavity on this graph here. Okay, so let's just focus on the first part, so up to point B. Am I concave up or concave down here? Concave down, right? Because it looks like the curve is opening towards like the bottom of the graph. So since this is pointing down, we're actually concave down. Okay, it's also written on the figure. Okay, from B to C looks like we're concave up because we're facing up. From C to D looks like we're concave down. D to E we're concave up, and so on. Okay. Now, let's just talk about our inflection points here. Okay. Let's talk about what's going on here. Okay. B, C, and even D are inflection points. Because at those specific points, we're switching from being concave down to concave up to concave down, and so on. Okay. So these guys here are definitely inflection points. Why is E not an inflection point? Or why is this point that I just drew not an inflection point? Michael?
It's not changing concavity.
Yeah, right. So over here, the second derivative actually doesn't exist here, but we're going from concave up to concave up. Okay, so there's no switch in concavity. This is not an inflection point. Okay. So that's not an inflection point. Now point P is an inflection point because we're switching from concave up to concave down. So this is an inflection point. Okay, and I think that's all I wanted to talk about here. Okay.
Point D, doesn't the second derivative technically not exist since it's a sharp?
Yeah, so I guess what we're gonna have to do is we're gonna have to think about why the second derivative doesn't exist also, which is a good point. Let me just make sure I talked about that here. Yeah, now I'm thinking about it, I'm like, did I actually talk about this? Getting scared. Yeah. Okay, honestly, in this class, when we deal with the second derivative stuff, I probably am not going to give you a function that's too hard to integrate, so you might not have to think about that at all. But yeah, even when the second derivative doesn't exist, I guess it could be an inflection point as well. Yeah, that's a good thing to note. All right. Yeah, so I guess when I said the second derivative exists, that was wrong of me to say. Thank you. All right, moving on then. Let's go to the second derivative test. Okay, so second derivative test also tells us about a local min or local max. So the second derivative test actually tells us the same thing that the first derivative of test tells us. It tells us if we have a local min or a local max. Okay, let's say f double prime, so the second derivative is continuous near a point. Hoping that C is either a local min or local max. Let's talk about this. Let's say that the derivative is equal to 0 at this point. So it looks like it's a critical value, right? And the second derivative is greater than 0. So we're concave up at that point. Then we definitely have a local minimum at C, okay? So if those two things are true, we have a local min. So second derivative positive, okay? Now, if the first derivative is 0, so we have a critical value here, and the second derivative is less than 0, so the second derivative is negative, okay? We have a local maximum at C, okay? So all we're doing for the second derivative test is we're finding our critical value, or at least the places where our derivative is equal to 0. We plug that value into the second derivative, and we figure out if it's positive or negative. Now, it's a little bit counterintuitive here because positive gives us a local min, while negative gives us a local max. Okay, I feel like that's a little counterintuitive here, something that you should probably know. Okay, now I didn't talk about what happens when the second derivative is equal to 0, right? What do you think happens then? It actually doesn't have to be an inflection point. We don't have to go from concave up to concave down. That's a good point. So what do you think the second derivative test tells us if the second derivative is equal to 0?
That there's a max level in the first derivative.
Not quite. So the first derivative is equal to 0. That tells us min or max, okay? What happens if the second derivative is not positive or negative? kind of a trick question. Second derivative test doesn't tell us anything, okay? So if, I didn't write this down, but if the second derivative of the point equals 0, then the second derivative test doesn't actually tell us anything, okay? So the second derivative test, it basically doesn't work, okay? Okay, so, okay, we have this really easy test for us. We can plug in the points, see if it's positive or negative. If it's positive, local min, negative, local max. But if it's equal to 0, then nothing happens. We're gonna have to do something else. Usually the first derivative test will work better, okay? I have a question for you. First and second derivative tests both tell us the same thing, tells us if we have a min or a max. Which one is easier to use?
You still have to use, you have to go through the second derivative. The first derivative to get to the second derivative, so technically the first derivative is most useful.
Okay, what if it's a polynomial and it's really easy to find the second derivative? Okay, honestly, it's kind of up to you here. To me, I think the second derivative test is easier. And I think when we'll do an example, you'll see that like plugging in numbers is a lot easier than setting up a number line and plugging in numbers, seeing if the derivative is positive or negative. I think the second derivative test is actually a lot easier than the first derivative test, okay? And let's just pretend we have my opinion that the second derivative test is easier. Why do we even have the first derivative test if I think the second derivative test is easier?
Because some things can't be second derived.
Okay, sometimes it's hard to find the second derivative. That's a good point. I'm actually going to write that down. Hard to find second derivative. But why also might it be better to use the first derivative test than the second derivative test? I kind of wrote something up here. Sometimes the second derivative test doesn't work, right? So sometimes I'm going to get myself in a situation where I plug something in to my second derivative and I'm going to get 0. It doesn't work there. I'm going to have to fall back on the first derivative test, okay? So even though the second derivative test might be easier to some of you, sometimes it doesn't work, okay? So sometimes it doesn't work. Okay, and because of these two reasons, either it's hard to find the second derivative, which is a valid excuse to not use it, and sometimes the second derivative test doesn't work. These two are reasons that we might want to fall back on the first derivative test. Okay, or I might just tell you straight up to use the first derivative test, and then I guess you'd have to use it. Okay, so let's go to the next page. I know this was a little bit abstract. I think it might make a little bit more sense if I kind of go through an example of using the test. I think it'll make us understand what it is a little bit better. Daniel, do you need the notes from last time? All right. So in this example, we have a polynomial curve, x to the 4th minus 4x cubed. I want you to discuss the curve with respect to concavity. I want you to find points of inflection, and I also want us to find some local maxes or mins. So to do this, I'm going to use the first derivative test, maybe the second derivative test, maybe some concavity. Let's just see what the question is asking us to do. Okay. Well, first of all, it's telling us to find the first and second derivatives of our function. Can someone tell me the first derivative of our function? All right. Minus 12x squared. Good. I think everyone got that one. All right, and finding our second derivative, what would the second derivative be?
Squared.
Perfect. All right, so just using the power rule. Usually with these functions, I'm not going to give you something too crazy because there's so many different things you're doing in each section. I'm pretty sure whenever I'm talking about concavity, inflection, something like that, you're probably going to get a polynomial. So that's kind of how it's going to be in this class. All right. Next up, we're going to find the critical numbers. So I guess we have to find places where something equals 0, right? Am I finding places where the first derivative equals 0 or the second derivative equals 0? First, right? Critical numbers is where the first derivative equals 0. So I'm going to take my f prime of x. I'm going to set that equal to 0, which means I'm taking my 4x cubed function minus the 12x squared function, equaling that to 0. How do I solve this?
Take out 4x squared.
Yeah, both of them have a 4x squared in common. This is usually how we go about questions that have like x's in both in all the terms. So we can take out a 4x squared. What would I be left with on the inside?
X minus 3.
X minus 3, good. Okay, so setting each of these to 0, the 4x squared will give me x equals 0, and the x minus 3 gives me an x equals 3. Okay, remember critical numbers, we also have to figure out where our derivative doesn't exist, right? So I have to find places where f prime doesn't exist. Well, polynomials exist everywhere, so we don't have to think about that. So it looks like our critical numbers are 0 and 3. And that's it. Okay. Let's go to part C. Part C says we want to find any local mins or max using the second derivative test. Okay. It says if necessary, use the first derivative test. And we'll talk about what that means a little bit later. Okay. So first, we're going to use the second derivative test. The second derivative test says we're going to take a look at all the places where the derivative equals 0, and then we're going to plug them into the second derivative. Okay. So essentially what we're doing is we're taking the critical values and not just any critical value, but the critical values where this first derivative equals 0, right? So where f prime of x equals 0, okay? And we're plugging them in to the second derivative, okay? So we're plugging them into f double prime of x, okay? All right, we got 0, we got 3. I'm gonna plug in f double prime of 0. I know that function is 12x squared minus 24x, so that's 12, 0 squared minus 24 times 0, and that gives me 0. Okay, I can also plug in f double prime of 3, and that's 12 times 3 squared minus 24 times 3. And I'm kind of bad at arithmetic, so I did this in my office, and I got 36. Okay, so that's what the second derivative test tells us to do. Okay. I'm going to start out with the x equals 3 here. I got 36, and 36 is bigger than 0, so it's positive. Okay, does that mean I have a local min or a local max at x equals 3?
Local min.
Local min, right? A positive second derivative means we have a local min. Okay, so this means local min. Okay, we'll talk about what the local min is after we figure out what everything is. Okay, let's talk about what happens at x equals 0. Here we have 0. What does the second derivative test tell us about this? Nothing. It doesn't tell us anything about the second derivative, about min or max. So here, the second derivative test actually fails. It doesn't tell us anything. Okay. So what do you think we're going to do with x equals 0? Yeah, let's use the first derivative test. Okay, now before when we use the first derivative test, we've found all the critical values, we set them up on a number line, and we tested every single value in between. Okay, I already know that x equals 3 gives me a local min, so I'm not going to put 3 on the number line because I already know what happens there. Okay, so what I'm going to do here is I'm going to set up my number line. Let me use a different color here, maybe like this red color here. And I'm going to draw a number line. Okay. I'm definitely looking at what happens at x equals 0, right? I already know what happens at 3. I'm gonna write it on the number line just because I want a number in between 0 and 3. But I already know what happens here. So already know what happens. But I don't know what happens at 0, so I definitely want to plug in numbers around there. Okay, so I want to use the first derivative test, which means I'm going to plug in 0 or plug in numbers around 0, right? What's a good number to plug in that's less than 0? -1, right? Let me get a different color here. So I'm going to plug in x equals -1. I'm using the first derivative test here. What am I plugging -1 into?
First derivative.
The first derivative. You can either memorize that for the first derivative test, or you can think about what it's actually doing. We're trying to figure out if the function is increasing or decreasing so we can figure out if we're getting a max or min, okay? So we're plugging this into the first derivative, okay? Now, I told you that if you have the factored version, you can do that. Let's do that then. Up in part B, we factored the first derivative. So I know that the first derivative is 4x squared times x minus 3. Okay. Plugging in -1, we have 4 times -1 squared times -1 minus 3. I know that -1 squared is 1. -1 minus 3 is -4. At this point, I don't actually need to figure out what the number is. Is this number going to be positive or negative? Negative, right? Because I have one negative in there. Okay, so that's all I need to know for the first derivative test there. All right, what's a good number between 0 and 3? 1, right? Plugging in 1 is a good idea. So I'm going to plug in x equals 1 into my first derivative, which is the 4x squared times x minus 3. That's 4 times 1 squared, which is 1, times 1 squared minus 3, which is, -2. Is this going to be negative or positive? Negative, right? Okay. So before 0 looks like I'm decreasing. After 0 looks like I'm also decreasing. Is this a local max or a local min? I hear a max. I hear.
It's negative on both sides. It's neither.
Yeah, we're going from something decreasing to something also decreasing. There's nothing turning around here, so nothing actually happens here, okay? You can either memorize that when you go from negative to negative, nothing's happening, or you can just think about something decreasing, going to decreasing, nothing's happening here. This is neither a local max or a local min. I guess we'll figure that out a little bit later, will we? But that's a good thing to think about. Okay, so nothing happens at x equals 0. We already know that there's a local min at 3. Let's figure out how we're going to write out our answer. Okay, so how do we say our answer? Let's write this in green. Okay, so our answer. Okay, would it be okay for me to say the local min is x equals 3? No, right? Or, I hear a yes. So is it okay to be like, okay, local min 3? Is that right? It's still not right. I guess you could say a local min at x equals 3, that would work, but WebAssign definitely wouldn't like that. The y value is usually what you like, or what we say, okay? So we can either say a local min happens at f of 3, because that's a y value, not an x value, okay? Or we could plug 3 into something. Am I plugging 3 into f prime, or f double prime? F, right? I want to find the actual function value. That's my local min. So I can literally plug it into my original function, which is 3 to the 4th power minus 4 times 3 cubed. And I won't make you do that in your calculator, but I think it's -27. Okay, so WebAssign probably won't take f of 3. I think it would kind of freak out by that. But what I would type in is -27 as my answer. Okay. As for our local max, looks like we don't have any, right? So there's no local maxes. Gosh, none. All right. Any questions on finding local mins or maxes using the second derivative test? All right. Let's move on to the next question, which is asking us about intervals of concavity. Okay, so we want to find out what intervals are concave up, which intervals are concave down. All right. All right. How do you think I'm going to find this? Yeah, right. I want to find places where my second derivative is equal to 0, because that tells us, okay, where my derivatives or my second derivative is going to be negative, where it's going to be positive. So the first thing we're going to do is take my second derivative and set it equal to 0. Okay. All right. Well, my second derivative is 12x squared minus 24x. I got that from part A. Okay. How should I solve this?
Take out a 12x.
Yeah, take out a 12x. What I'd be left with on the inside is x minus 2. Okay, looks like the 12x gives me the x equals 0, and the x minus 2 gives me x equals 2. Okay, now I probably won't give you a function that requires you to do this. Usually I'm going to give you polynomials for concavity, at least because there's so much going on here. But you also kind of want to look for places where the second derivative doesn't exist. Okay, and the reason because of this is because if I graph my second derivative, okay, so if I show what my second derivative looks like, and I have a discontinuity, okay, so where my function doesn't exist, I could be concave up on the left-hand side, and I could be, concave down on the left and concave up on the right, okay? So that could be a thing that happens, and if my function doesn't exist, I'm not concave down or up where there's no function, okay? So you do want to look for places where the second derivative doesn't exist, but I'm probably going to give you polynomials, so don't really need to think about that. All right. So it looks like we have 2 candidates for switching between concave up and concave down. So maybe I'll make a number line. Okay. Kind of like the first derivative test tells me to do. How I found my intervals of increasing and decreasing. I'm going to put 0 and 2 up here. And looks like I'm going to start plugging in numbers. All right. What's a good number to plug in that's less than 0? -1, right? And what am I going to plug -1 into? Original function, first derivative, second derivative. Well, let's think about what we're doing. I'm trying to figure out if I'm concave up or concave down. What function tells me about concavity? The second derivative, right? I want to know if my second derivative is positive, which tells me I'm concave up, or negative, which tells me I'm concave down. So you can either memorize how to do this, or you can think about, okay, I'm thinking about concavity, second derivative tells me about concavity, so I'm plugging this into the second derivative, okay? Now I have a couple options. The second derivative is 12x squared minus 24x, but I did factor it, which makes it a little bit easier, okay? So I'm gonna use the 12x times x minus 2 version, okay? So it looks like we got 12 times -1. -1 minus 2 is -3. Is this gonna be a positive or a negative number? Positive, good, okay? Because I'm positive, am I gonna be concave up or concave down? Concave up, good. So concave up here. Okay. I'm gonna do this one, plugging in a number between 0 and 2. Well, 1 is a good one to plug in, right? If you tell me to plug in a different number, I'm gonna dock your grade by like 10 points. All right, and I'm plugging that into the second derivative. So this becomes 12 times 1 times 1 minus 2, which is -1. Yep. Is this going to be positive or negative? Negative, so we're concave down. Okay, and then plugging in x equals 2. Looks like we got 12. Oh, sorry, not x equals 2. What's a number greater than 2? 3, right? Okay, 12 times 3 times 3 minus 2, which is 1. Looks like we got positive, so we're concave up. Okay, so we're going from up to down to up. All right, so let's talk about intervals of concavity. So let's write our final answer here. Okay, we want to find intervals where we're concave up. Okay, I know I'm concave up from negative infinity to 0, right? Negative infinity to 0. Infinities always get a parentheses. Should I use a parentheses or a bracket for the 0? Parentheses, right? The derivative or the second derivative is equal to 0 at 0, so we're not concave up or concave down at x equals 0. So because of that, we're using a parentheses. Okay, same thing goes with the other side. So we're going from 2 to infinity. Okay, using parentheses for those. Rule of thumb for these guys: concave up, concave down, or increasing, decreasing. We're always using parentheses for these because, well, we're figuring out if the derivative is equal to 0. Can't be concave up or concave down where that happens. All right, concave down. Pretty sure you guys know that this would be between 0 and 2 with parentheses. So that's how I would type in my answer to WebAssign. All right. Any questions on part D? All right, finally, let's talk about inflection points and how we can write our answer when we're talking about inflection points. So let's do part E here. Inflection points are where we switch from concave up to concave down, right? That's the definition of an inflection point. So here you're going to look for, oh my gosh, for, oh my goodness, where we switch from concave up to concave down or concave down to concave up, right? And as John said, okay, maybe the second derivative might not exist there. And questions like these, don't even think about it because I'm going to give you a polynomial. Okay, where do we switch from concave up to concave down? 0 and 2, right? You just take a look at the question above. Part D says at 0 and 2, we do switch from concave up to concave down, okay? So we know this happens at x equals 0 and x equals 2, okay? Do you think that's going to be my answer? No, right? Let's just talk about what the answer is going to look like. I am asking for an inflection point, right? So what do you think my answer is going to be? A point, right? An x and y coordinate. That's what a point is, right? So a point is an x and y coordinate. Okay, so my answer for an inflection point is going to look like a parentheses with the x value in the first part and the y value in the second part. Okay, so it looks like I'm going to have to plug something in to a function. Okay, so I'm going to plug in x equals 0 and 2. Am I going to plug it into f prime, or f, right? We're looking for a point on the function, so we're plugging it into f. Okay, so we're plugging it into f. Okay, so I'm going to do f of 0. Remember, my original function is x to the 4th minus 4x cubed, so that's the function I'm plugging it into. Looks like I'm going to get 0 here. Okay, looks like I have f, I'm plugging f of 2 for my other one, so that's 2 to the 4th minus 4 times 2 cubed, and that gives me negative 16. Okay, so it looks like I've got 2 inflection points, right? My inflection points are, and it's very important that they're in coordinate form, especially for typing it into WebAssign. Okay, I promise WebAssign wants you to type in the coordinates. 0, 0 is one of my coordinates, and 2, negative 16 is my second coordinate. Okay, so it looks like I have, oh my goodness, 2 inflection points going on here. All right. Any questions on any of these problems here? All right, I think you have enough to do the homework for Wednesday. We'll do another example next class on this. It's basically the same thing, except the question's a little bit harder, but not too bad. I think you have enough to do the homework, so I'll still have it due on Wednesday. Wednesday, we'll do another example and we'll start talking about L'Hopital's rule, which is kind of interesting to think about.